Bluetooth. Get it straight.
Here's a couple of hints for homework number 7. And skipping the first two, I think we went over some examples in class that should be good enough to get you going on those. Problem 3 is a problem where you're given a velocity potential here, and it's a pretty simple function of both x and y. And we have to use our definitions here. First step is to use the definitions of the velocity potential to get your v and your u components. So that you probably figured out. But the harder part really is to go back to Euler's, because you're asked to show this issue up here. So you're asked to show that, and so we need to take steady and viscid flow, which is what you need in order to even have a velocity potential. You can't have it if you don't have steady and viscid flow. That's Euler's equation in 2D. Got x and y components. So we've written it all out here, and then we cross out the ones that are 0, which is gravity here, since we are in the, I think, in the horizontal xy plane. Gravity is not a factor with respect to the x direction. So if we're just looking at the x direction, we end up with this dp dx term, which is good because that's what we want up here in the question. So after you've gotten all done with all the Euler stuff, you should end up with something that looks sort of like this. And you can take it from there. The next one, we're starting to get into plane potential problems. So these were the last thing we talked about on Thursday. So in this case, it's key to think of the geometry, which is kind of given to you in the drawing. But just drawing it out neatly here, we have a flow field coming in. There's a little pump here that's taking flow down the hatch here, and we orient things near this hole with r and theta. So we use the cylindrical coordinates, and we can recognize that this is a uniform flow field coming along, looking just uniform because it's not affected by the pump until it gets near the hole. And then at the hole we have a sink, so we have the sink here. So our two stream functions are uniform flow and sink. Now a tricky part here that kind of comes from experience really is that because our sink is really for a whole system, our sink would be taking things from the side as shown, but it's also taking things from the other side too. When you say sink, it says it should be coming from all sides. So basically what you have here is a half sink. And so the value that's given of 1 cubic foot per second is for the half sink. So in order to make it be 0.1 cubic feet per second and be a half sink, we should assign 0.2 cubic feet per second to the solution of the whole sink. Then we'll get the half of the power over here and half the power over here. And lastly, we have the car windshield problem. I won't tell you too much on this one, but from the geometry, you can kind of figure out from your trig there that this distance b from the origin of your reference system, again, we're in cylindrical coordinates with theta and r, but b out in front of this is plus r cosine theta would be equal to 2 feet. So that's this line plus this line basically equals 2 feet. And so, and then also r sine theta is 1.5 feet. That comes just from this triangle over here, side. So other than that, we have to recognize that this is a half body problem, and the flow's a uniform flow coming out here. We almost always have a uniform flow plus something, but in this case we have a uniform flow plus a half body. So I hope those hints will help, or that you're already done, and good luck.